Hi everyone, I'm Valerie Brogdon, a new member of the team here at Covalent Metrology, and I'm here today to tell you all about the past, present, and future of TEM prep. So as we all know, TEM is crucial in semiconductor manufacturing. TEM is the only technique that can provide atomic scale imaging, which is essential for analyzing the structures in modern semiconductors where features can be just a few nanometers in size. TEM allows us to directly observe defects in crystal structures, such as dislocations, voids, impurities. All of these can cause major problems with performance and yield. When used alongside techniques like EDS and EELS, TEM can also provide elemental mapping, which helps manufacturers understand the chemical composition of devices. And when semiconductor devices fail, TEM data helps engineers understand the root cause by providing detailed images of the failure site. Semiconductor fabrication involves hundreds of complex steps, including deposition, etching, doping, CMP, and so on, and TEM is used to verify if these processes have been executed correctly. It can help measure layer thickness, uniformity, interface quality between different materials, grain structure, and more. TEM plays a crucial role in ensuring that the semiconductor manufacturing process is precise, defect-free, and able to meet the demands of increasingly smaller, faster, and more efficient devices. However, preparing samples from a bulk semiconductor chip that are thin enough for TEM analysis has never been trivial. It's a process that engineers have been improving on for decades now with a few big goals in mind. As devices get smaller, TEM lamella need to be thinner and more precisely placed. Furthermore, big semiconductor companies like Samsung and Intel are preparing hundreds, if not thousands, of lamella a day. So the process also needs to be very fast and with low or ideally no training required. So let's take a quick look at the history of TEM prep and how much it's changed in the last few decades. And here are some of the first ways that researchers were making TEM lamella. So the edge fracture technique, which I'm showing on this slide, is maybe the oldest technique for TEM prep. It involves fracturing the sample and taking advantage of the fact that multi-layered devices typically don't fracture cleanly through all the layers, but one layer will be set back a bit from the next. So after this uneven fracture, a heavy metal is deposited at an angle, which creates this shadowing effect, depending on the height of the layer right next to it. And then a thin carbon film is evaporated on top, and chemical etching is used to peel off of that film. And that right there, that strip, that was your TEM lamella. That's what gets imaged in the TEM. And apparently people were able to glean some useful information from that. Okay, and then there's the horizontal section technique, where a sample is mechanically lapped on both sides with grit paper until it's about 100 microns thick. And then the sample is mounted on transparent sapphire, and wax is used to cover and protect the areas that you don't want to be etched, because we're going to do acid etching next, and wax is resistant to acid etching. So then you chemically etch the whole thing until a little hole opens up, and the taper around the hole is generally thought to be thin enough for TEM. And another technique that was used in the 70s was to embed the whole sample in epoxy and mechanically polish it with grit paper until it's about 100 microns thick. And then they would ion mill it until a small hole opens up. And again, that taper around the hole is thin enough for TEM. And then in the 80s, tripod polishing came out. So this process involves mounting a small sample onto this three-legged polishing jig that you see here. And it provides really precise control over the polishing angle and pressure. And then the sample is mechanically polished using finer and finer abrasives while maintaining a shallow angle between the sample and the polishing surface so that the sample kind of tapers with the thinnest area being out here on the edge. And then that's often followed by ion milling for the final thinning, which by the 80s had also gotten a lot better since the 70s. But the problem with all of these techniques from the 70s and 80s is that they aren't site specific, they aren't fast, and they kind of require a lot of skill and training. They're really more of a art or a craft. So then in the 90s, people started using fibs for TEM prep, but manipulator probes that were built into the fib didn't exist yet. So they had to put the lamella on a grid outside of the fib sim. And there were two options for this. Either you could get the sample really thin inside of the bulk substrate and then take it out of the SemFib and put it onto a TEM grid. And this is done under an optical microscope using a glass rod. Or you could do the H-bar method, which requires that you mechanically polish the sample as thin as possible using a tripod polisher, and then fasten that chunk to a grid, and then use fib to just open up this little thin window right here for the final thinning. So in this version, we put it on the grid after we thin it, and on this version, we put it on the grid before we thin it. And then in the late 90s, people started figuring out how to use probes that were built into the fib sim to do lift outs in situ. And the first fib lift out is a little bit hazy. So in the US, a lot of people attribute the first ever fib lift out to Lucille Giannuzzi. And if you don't know Lucille, she is an absolute fib legend. She literally wrote the book on fib. It's magenta, which I think must be her favorite color. And I have a copy at home. She has tons of patents on fib technology. And most recently, she started a company that makes a lift out tool that we actually have here at Covalent. And I'll talk about that a bit later. So as I was saying, a lot of people in the USA attribute the first fib lift out to Lucille. However, a couple of years ago, when I was at a FibSim conference, I met Tsuyoshi Onishi, who works at Hitachi, and he is this cool old Japanese guy, and he told me that he was actually the one who did the first ever fib lift out in Japan, and the application was for circuit edit. He was doing transplant surgery on one wafer, so he would bulk out the functional part of one wafer and then lift out that defective part and insert a functional part on another wafer. And I looked into this and I found his paper published in the Japanese Journal of Applied Physics. And sure enough, he was doing fib lift outs nearly a decade before anyone in the US thought to try this technique for TEM sample prep. And Onishi-san is also a fib legend in his own right. He and his team at Hitachi actually came out to my old lab at Camcor to check out some of my inventions to talk about Hitachi potentially licensing them. And when I reached out to him to ask about his fib history, he sent me this cool image of him in 1984 next to a fib that he built when he was in grad school. And it's such a cool picture that I just have to include it here. So I feel very lucky to be personally acquainted with both of these fib legends who really shaped the field for all of us. So nowadays we have manipulators and gas injectors built into the fib sim. So the current state of the art is to do the lift out, grid attachment, and final thinning all inside of the fib sim. And there have been all kinds of innovations to make low energy fib beams tighter and more collimated so that the sample can be even thinner with less of a damage layer. Okay, so this is good. Now we're getting somewhere. Now we can get very site specific and also very thin. And it's also relatively fast, but it's still very high skill and it could be faster. So to increase ease of use and eliminate the training problem, the next big hurdle was to get this process fully automated, with the idea being that you load a sample into the SemFib, punch in how many lamella you want and where you want them, and then you come back later to a bunch of thin lamella. So FEI was the first to patent this process back in 2017. And not to brag, but I was the lead engineer on this project and I'm the first author on this patent. So I spent a lot of time figuring out how to get TEM prep fully automated. I literally sat in a basement and did nothing but work on an automation script that chunks out samples and puts them on grids for about 3 years. And that is why I know that one of the biggest bottlenecks to increasing TEM prep throughput is the manipulator probe. So let's go through some of the challenges with the manipulator. First of all, every time you prep a lamella, the needle gets a little bit shorter because you need to cut the needle free from the lamella after you attach it to the grid. And eventually, it will reach the mechanical limits of motion, and users need to vent the system to change or adjust the needle. Also, if you run a university lab like I did, you'll get novice users who accidentally ram the easy lift into the stage and bend it. Or maybe it gets bent because you deliberately land the needle on the stage because you need to ground the sample. Or maybe it gets bent because you're using the manipulator for something kind of weird, like I was in these two images when I was poking this tiny sphere to find out that it was even full of tinier spheres. So this is actually a slow-release drug that would melt whenever I tried to fib cross-section it, so I just decided to stab it open. But after this, my manipulator needle was all bent, and it was also covered with tiny spheres, so I needed to vent the system and change my needle. And then, once you go to vent the tool and change the needle alignment procedure is extremely error-prone. Up until very recent fib models, there was no hard stop on the needle holder. So users need to stand directly over the needle and look down on it through a magnifying glass and then nudge the needle back and forth until the very tip of the needle is right on that black-white transition. And we are talking about trying to align a 1 micron diameter needle tip to within about 500 microns of that black-white transition. So even for expert users, this process often takes multiple attempts, which means multiple vent pump cycles, which wastes a lot of time. So we're ending up with lots of vent pump cycles, which slow down productivity, increase tool downtime, and also increases tool contamination. So what we really need is the ability to feed more length of needle into the tool and then fib sharpen it. So that's exactly what I invented at my lab. We created some new hardware for the manipulator probe, which allows users to twist a knob on the outside of the chamber, which will extend the needle further into the chamber or shorten the length of the probe if it's twisted in the other direction. And here is a video of the extendable probe in action. So when I want to drive the needle further into the chamber, I just do this. Twist, 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 and look what's happening. Great. So now you've seen it in action. So we have a Helios 600i, and it came with an Easy Lift nano manipulator, so we just took that rod out and replaced it with a rod of our own design. And this is a really simple invention that's already ended up saving us tons of needles and time that would have been spent venting and pumping the tool. And if for some reason we do need to change the needle, this invention majorly simplifies the needle loading process because now you don't have to worry about using the magnifying glass to get the needle right at the black-white transition. It doesn't matter if the needle is too far out or too far in because you can just twist the knob and adjust the needle position while live imaging with the SimFib. So if you'd like this innovation in your lab, let me know. My former colleagues at U of O and I would be happy to get one of these fabricated for you, and you can test it out and give us feedback. Let us know if you have any suggestions for improvement. It's really fun for me to come up with solutions like this and see the different ways that people use them. So I would love to get this thing installed in more labs. But of course, innovation doesn't stop there. So in parallel, Thermo Fisher has been working on their own solutions for some of these problems. And while some of the challenges that my invention solves have been addressed with this new tool, others do remain. But their brand new Helios 6 platform, I have to admit, is very slick. It takes TEM prep to a whole nother level. And we're very proud to be the first service lab in the USA to install it here at Covalent. So let's take a look at some of the features that are really moving the needle, literally and figuratively, in terms of speed, efficiency, and sample quality. So first of all, there is now a hard stop in the needle insertion. So users no longer need to use this magnifying glass and squint their eyes while they wiggle the needle back and forth, because you can just push the needle in until it stops and call it good. So that's a huge ease of use thing. Also, there's a new multi-chem design, and it's got better thermal management. The crucible design has been optimized, and probably most importantly, there's a new flange, and the flange design prevents drift. And that means the needle's not getting closer or further away from your sample. And that makes for much more stable depositions. And that's going to definitely help when you're writing automation scripts if you know your deposition is always going to be the exact same thickness. And then, of course, there's the new Osprey column. So the new column has improved motors to steer the LMIS around and lots of hardware improvements on the suppressor. It's also got some software innovations to monitor the LMIS motor, and it's got a new digital deflection board to make the measured resolution a lot better. So let's talk about SEM immersion mode if you're unfamiliar with it. A lot of us know it to be high resolution mode, but I just want to show you what it does really quick. So what happens when you're in normal mode or field free mode is the lens is inside of the column like this. But when you turn on immersion mode, what you're doing is you're immersing your entire sample in a magnetic field. And that effectively creates a lens a lot closer to your sample surface, so you can get a much tighter spot on your sample. And this results in better high resolution imaging. So in the past, when you were working with the fib and making cuts, and then you went to go turn on immersion mode, the beam would just deflect like that. So anytime you wanted to take an image in immersion mode while you were thinning with the fib, which is exactly what you want to do at the final thinning steps of TEM prep, you want to be as high resolution in the SEM as possible to target these tiny little features that you're trying to endpoint on. It was kind of annoying because it really took a long time to switch between the fib and the SEM. But now there's corrective optics that when you turn on immersion mode, it steers the beam back into place. So that results in just improved endpointing. So the Helio 6 HD has ultra high resolution imaging while you're milling. And you don't even have to use the iSpy feature and pause the fib while you're milling. You can actually live image while you're cutting. And I'll show you a video of that. Oh, great, there's a video here. Okay, let's see this. It's cool. This is a FinFET device. You can see the little fins there, the gate all around it. And this is an inverted sample, so the silicon's on top. Okay, and they're starting the fib mill. Cranking up the beam current. Notice over here that we are in immersion mode and we're in fib immersion mode. Yeah, so this is great. We're just live imaging with the SEM while we're milling material away. This is a very powerful new ability. This is going to help us a lot to endpoint when you want to end like on exactly one gate. And I'm just going to skip ahead because I also have a movie here that goes a little bit faster. So you can see these gates and these little fins kind of retreat in real time. So Thermal also made some significant improvements to the scanning engine so that when you initially set up your cut location or even the scan rotation that you're using during thinning, it's now extremely accurate. And you can perfectly align the image from left to right so that you know that you are cutting through this same gate all the way across. And this is a very large image for STEM. This is actually several STEM images stitched together. And I don't know exactly what technology node this is, but this is very obviously a FinFET. And you can see here that this person sliced directly through the center of 16 different gates. So when you're dealing with features this small that are all in a perfect horizontal line like this, even the tiniest bit of rotational offset is going to cause you to miss a lot of targets. So getting this scan rotation right is a really big deal. Furthermore, there have been a lot of improvements to AutoTEM. So AutoTEM is now smarter, faster, and easier to use, and it integrates with AI and it uses machine vision to help you set up all of your grid positions beforehand. However, even if you get TEM prep fully automated, there are still a ton of steps for doing in situ lift out. You have to weld the needle to the sample, cut it free, lift it out, line up your grid, prepare your grid, drive the needle down to the sample, weld the sample to the grid, cut the needle free, retract the needle, and then I always flip it over and also weld the backside in addition, because I want to make sure it really sticks. So as you can see, there are a few downsides to in situ lift out. Not only is it time consuming and fairly high skill with lots of steps, but all the extra fibbing directly on the face of the sample could cause a lot of damage. Plus, the fact that we need to access the top of the grid to do the drop off and the fib limits the amount of samples that we can fit on any individual grid. Of course, the way that people have tried to address the grid capacity problem is by adding more posts to the grids. You see, it started with 4, and then we had 5, and now we have 8. A few years back, my colleague Rob Routh and I actually patented a new grid design where every post has this stair-step shape so that you could put several lamella on each post. You see, put one here, put one here, put one here. But it never really caught on, and I think people were worried about redeposition. If you're thinning this lamella, is it going to get redep on that lamella? Maybe. I'm not sure. But then Lucille Giannuzzi came along and ate all of our lunches when she solved all the problems with fib lift out at the same time by simply going back to ex situ lift out. So here at Covalent, we have her Express LO Nicola product. It's also got a lot of magenta on it in true Lucille style. So Nicola stands for Not in Column Lift Out Apparatus, if you didn't know that already. So this is a really simple device that just uses a glass rod to lift out samples and drop them off on the grid. And here is a movie of it in action, so you can see how fast it is to do the drop off. I think she's going to pull this off in like 30 seconds. Yeah, it's got a little built-in microscope, motorized lens changer, motorized manipulators. Okay, pick up the sample. Move to your saved stage position on the grid. And then you just bring it down. And set it right on top of the grid. So she did that in 28 seconds. Pretty impressive. So there are some downsides to dropping a lamella off on a lacy carbon grid, kind of like she did in that video. So first of all, carbon contributes to low-level background in eels and ES. And that's going to reduce signal to noise for very light element quantification. Also, thin films can wrinkle and sag, especially if you do a plasma cleaning or any kind of vacuum cycling, and that can cause local thickness variations and also contrast issues. Also, carbon is prone to hydrocarbon deposition under the electron beam, and that leads to buildup over time, especially when you're doing high-resolution imaging. And if not grounded well, carbon can contribute to mechanical or electrostatic drift, and that affects high-resolution STEM and holography. And also, amorphous carbon may introduce low-level phase contrast, which can obscure very weak or fine features. So that's why the brilliant Lucille came up with this new grid design, and it's one of those things that's genius just because it's so simple. So how it works is the edges of this grid are beveled so that the sample gets wedged right into this funnel shape. And it's just a friction fit. And apparently it stays there pretty good. So nowadays, actually we're going back to ex situ lift out because the fastest way to crank out a bunch of lamella are to thin them down in the bulk substrate and then vent the tool, take them out, and just pluck them out one after the other with the XLO tool. So, with the recent acquisitions of both the Helio 6 and the XLO Nikola tool, Covalent is positioned to be at the forefront of speed and efficiency when it comes to TEM prep. So, we are really proud and excited to just be here shaping this field with the rest of you. So thank you so much. I am now available for questions, and feel free to jot down my email address. And if you ever have any questions or comments for me, just reach out or find me on LinkedIn, whatever you want to do. I love nerding out about fib. So don't be shy.